Okay, lesson 12, part 2. Actually, look at our code. You need to make sure you've seen part 1 to have any idea what we're going to be talking about in part 2. So, we have a lot to cover, and hopefully, we get it all done in one part. Don't know. Let's start with our basic program. Again, we looked at it before. You have to see in part 1 to understand the mechanism getting from here to the assembly language program. We won't cover that again here, but we'll look at our program starting here. We got some variables up here. We got number of loops. I'm just going to LP with 30 loops. So whenever we're doing something, we're drawing circles or boxes or lines. We'll do them 30 of them. We got some deltas. We got some maximum screen width, screen height type things there. Start out, we're going to go I'm going to have to go through some of this here. 870, I didn't put a note in there. I know what that is. That's down here at 870. We're going to set up the palettes. In the past, we've always set up the palettes the same way. In our assembly language program, we're going to set them up exactly the same way, them same colors, the reds and the greens and the yellows and the blues. Same exact way as we did in the, I said in the assembly language program, we're just going to do it here. So we're going to go, here's the colors down here, our black and our blue and our, which order, and here's a red down here, here's a yellow, a white, and a yellow. Anyway, we're going to put them in the palettes 0 through 7 and 8 through 15, and do that, set the palette, and we'll do basically our background color of white, foreground color white, the background color of 0. So that's what that go set was. It's just setting up our palette. Okay, then we're going to tell to do our H screen 190, 320, 192, 16 colors. And now here's the main menu, or the main, it's also the main loop. Very first thing is we're going to go off to our assembly language program, user 0, which is a clear screen, okay? You may say, well, why don't we just do an HCLS to clear the screen? And I will tell you why later, but right now I won't. We're just going to go off, we're going to do the clear screen on our own inside the assembly language program. Right? Again, we're setting the background color, same we did below, but this is the main loop, and every time we come in this loop, we want to set this to background of black and a foreground of white. And then we'll print all this stuff on the screen like you've done before. This is for our selection. We'll wait until we get our selection, and then we'll clear the screen again. We'll get rid of that, and we're going to do one of these items here. I know you can make this here on one line, go to based on something, but for a class or a lesson, it's easier to spell it out here so you don't have to guess at what a 5 is doing. It's just, because if I say if a 5 is go to 690, you wouldn't know what that is, but here I can look at here, it's going to the message routine. So anyway, this is the loop. Clear the screen, put this on there, and then get one of the things coming in from the screen, and go do that. Okay. So, and each one is different. Okay. Here's the lines routine. I got a lot of remarks in here, which I know cuts down a lot of time in your basic program, but at least we'll be able to read it easier. In the line, just says a loop. From 1 is a LP. Our loop was 30, so we'll do 30. Get a random color and draw a line with some random coordinates, X, Y coordinates. Set on the screen and draw them 30 and go back, and 790, all 790 is a get key routine, so it's not, get common routine goes back to 130, goes back to the main loop. So it's just going to keep looping through there. Find out what you want to do. You do this init, the start, whatever. And each one of these, they're pretty much all the same. Here's the lines. Here's the code for the circles. Here's the boxes. Okay. The init's the same. All a init does is goes off to the assembly language program by this method we learned in the last lesson. Go off and do the init and come back here and go with 130 is go back and do the routine in the main loop again. Same with start, stop, speed. They're all the same. The only thing one is now is different is message. Hit message, it's going to draw a circle, draw a line, draw a box. It's going to all three of them on the screen. And I know why I did that. I just did it so that we can have this all combine and work together. So message, we'll put them all on the screen. We'll change our background color back to normal, and we'll do a line input okay, which is a variable, a text line input. From the screen we'll get it, and going off to the user routine, remember I look right up here at 670. User routine is our variables are numeric, so we'll use X and 0. Down here it's string data, okay, so we have to use the $sign. So we're going to pass it when we say it's X equals, or X $sign equals user, and pass it as string data. And when we get over to the assembly language program, we'll look at what does that mean, because the assembly language program is going to take that variable passed to it and print it on the basic screen. Okay, so it's a little different than the rest of them. Well, the exit also is a little bit different. It's going to draw a circle. It's going to set up that variable pointer and pass that off to the assembly language program to a different routine and end the job. So that's the basic program. It's very, very simple program. Very well. I got it drawn out here with hopefully a lot of remarks so you can look at it and you can probably improve it. And hopefully I'm going to give you a challenge at the end of this second lesson or third, whichever how long it takes. Give you a challenge to improve this, because this code has no, the assembly language program in this basic program has no error checking. Very easy to break it, okay, unless you do things in a certain order. So my challenge is going to be, and I'll point out what you can probably do, is to put some error checking routines in there, because there's none in here. Because right now you could come in here and start this program up and say start without a init in it, and you're done. You're lost in never land. Likewise, you could come in here and say init, and you're going to be screwed up when you exit, because you should only do one init. Likewise, if you come in and just say, I don't want to do it, I've changed my mind, I'm going to do an exit, you're screwed again because the code isn't there. So anyway, I'll give you a challenge at the end. So that's the basic program. It's pretty simple and can use some error detection routines in there. All right, let's look at our assembly language program now. All right, it's kind of the same thing we've done in the past. It all look the same. We're going to include that common routine. It's that common include, which I've given to you many times, and use that. We'll get down to our program. We got a starting address 7800. If you recollect, that's what where our 8 extra lines start at. We'll use that later. Again, here's our routines coming in from BASIC, which will come down, and we'll look at the code for these routines now. Okay, our first routine says set up IRQ vector, and the init routine. Really, it's more than the IRQ vector. It's setting that up, but it's setting up everything that we're going to do within this assembly language program. We're going to load up our starting address. If you recollect, it was 7800, which was that band of we're working our extra 8 lines in, and we're going to store it for our starting address. Then we're going to turn off all interrupts. We're going to turn off the CPU to not accept any interrupts. Okay, we don't want to be interrupted while we're doing what we're doing. Next thing is we're going to load up 3E. Remember from lesson 1 what 3E was? Well, let's do a memory refresh while we're here and go back to our graphics screen. 3E was this little code right down here, which sets us to 320 by 200 by 16 colors. All right, we got that, our 3E, and we're going to store that in our video register, FF99, that says, here's what I want you to display on the screen. So now the MMU, as soon as we do that, we'll start displaying them extra 8 lines on the screen. Basic not knowing what we've done. And next we're going to disable the IRQ and the FIRQ, that's the interrupt vector interrupts on the MMU. Okay, we disabled up here the CPU to ignore all interrupts, and we're disabling the MMU, which is other interrupts. Don't even put out an interrupt for the time being. So we do that. So we're not going to put out an interrupt. And we're down here. This line here says for keyboard interrupts 02, for timer 20, 22 for both of them. Well, it's been kind of debunked or proven that the keyboard interrupt does not work correctly. There's not a lot of documentation on it. I've tried and tried and tried. I know with MES and MAME it does not work at all, but it doesn't work correctly. It seems to work on VCC, and I have no idea on a real machine or X-ray. I have no idea, but keyboard doesn't work. So don't try. You can try to use it, but it don't work. Excuse me. So we're going to be using the timer interrupt only. So we're going to load a 20 in there and store it, and that will enable the IRQ. Okay, we're going to talk a little bit more about interrupts, so don't let the language scare you too much. So we disabled them both up here. We just disabled everything, and we say if you do an interrupt, we only want an interrupt coming from the timer. We haven't turned it back on. It's the only thing we want you to do whenever you do them is the timer one. Now we're going to do our interrupt vector. Okay, what is an interrupt vector? Okay, if you haven't done interrupts, an interrupt is, you get an interrupt for multiple things. It interrupts, it tells the CPU, interrupt whatever you're working on and go to a service routine and do something else. And when you get done with that something else, come back and where you let off, we'll go right on from there. And it can be for a number of things. If you're working with a disk drive, okay, you'll get an interrupt coming back when it's found the correct sector. Okay, I'll just use that whenever it's found it, because if you're working on a disk drive that's spinning around, when you say read it, you don't know where the head is at in relationship to the disk spinning around. And if you're, I don't know how fast they go on a color for more, just say they're turned at 700 to 800 RPMs, you have a split second there to wait until that record comes back underneath the head. When it gets it, you're going to get an interrupt back. Yeah, I'm used to working with mainframes, how they work. And if you got a terminal coming in, you get an interrupt on a terminal and somebody does something. There can be many things causing interrupts. Outside interrupts tells the CPU stop what you're doing, go over, service this interrupt, do whatever it's supposed to with that interrupt, and then come back to the program that's currently working. It will finish the instructions. So I'm going to just look at right here what we're doing. We're down here right here in this line 32. If I'm doing this load X to this interrupt vector, this particular instruction, and the interrupt comes in, it will finish that instruction. It will load X with that, and then it will go off to someplace you don't know anything about. It will do something, whatever that something is, and then it will come back and it will execute the next instruction. That's what an interrupt does. The interrupt vector is tell it, where do you want to go? Okay, so we're going to tell it where we want to go. Now, I got this FB F7. You say, how in the heck would you know about that? Well, if you've listened before and you've done some of the things they ask you to do, is get BASIC unraveled. Okay, from Color Computer Archives, they got all the basic programs. Color Basic, Disk Basic, Color Computer 3. I guess that's super basic. You got unraveled. It's under, and if you look in there and you get down to this section by interrupt vectors, you're going to read about it a little bit in here, and this is where they're at. On a Color Computer 2, it's got a list in here, and a Color Computer 3. Okay, we're on a Color Computer 3, so here's the vector. Remember, vector is where that interrupt, when it happens, where do you go? And it's here is where you go. But we're going to use an IRQ. We're not going to use it. There's a difference. There's a fast one and a normal one. I don't want to get into too much of that. We're going to use the normal interrupt. All it does is it saves all the registers for you and restores all the registers like nothing ever happened. The fast one doesn't save all the registers, only partial, so you could have a mess if you're on your hands if you're expecting to be like. So we'll look at this line right here. Okay, the regular color computer vector is at 10C, and color computer 3 it's at FE F7. This is found in color super basic, I think it was super extended unraveled. Get it and read this whole section in there, and you'll maybe understand a little more. Do a search out there for interrupts, and you can learn a lot more. So here was that FE F7. We're going to load up that address, and at FE F7, here, right down here, I've typed this code in, I've added it so you can see it. Here's what's at that. We're going to take them 3 bytes. It's got this here 160212, which if you disassemble that, it turns out to be a long branch to 01 Charlie. Okay, so whenever an interrupt happens, this interrupt vector at FE7 will all branch to this 10 Charlie. I mean, it's a branch to branch to branch, okay, but that's okay. We want to save these 3 bytes of address and restore it when we're done, and put our own address to where to go. So up here, we're going to load up the address of where that current vector is, and we're going to save it in a place on our program called Save IRQ, and that's all the way down here at the bottom. I'm going to show you there's 3 bytes down here. We're going to store them 3 bytes to save the IRQ down here. So take them 3 bytes, and that's all we're doing here. We're going to load up the first byte and store it in our save area. We're going to load up a jump instruction, which is 7E, and we're going to store it in the first byte of that old vector. And then we're going to load up the original 2 bytes from that vector and save it in our area. And we're going to load up an address called myIRQ. Okay, this is the new routine, and we're going to store it. Okay, and myIRQ is our interrupt routine. Here's our code that we're going to be doing. All the stuff on the screen is at myIRQ. So we're going to save 3 bytes and put 3 bytes in there. That's all it's doing. It's just trying to explain so you understand what the interrupt's doing and what the vector does. So at this point now, when an interrupt comes in, remember we got them turned off. When an interrupt comes in, it's going to, and they're turned on, they're going to go to our routine. All interrupts will go to our routine. Okay. Here's the that double speed poke. This here's some I asterisk this code out. You can change the value of the timer. I've started to play with it. I forgot to take that out. And then here again, we're going to enable interrupts and return back to the basic program. So at this point now, we've done some things. Let's retrace what we did. We turned the interrupts off. We disabled the interrupts on the MMU. We told it whenever we enable it again, we only want to use the timer. We changed the interrupt vector to go to our routine whenever there's an interrupt, and we turn the interrupts back on. So other interrupts now coming in will go to our routine. So let's assume that in our program we're not using a disk drive, but we do something to the disk drive and we get an interrupt back from the disk drive. What's it going to do? It's going to go to our routine. Why would it do that? Because we told it any interrupt, go to our routine. Okay, here's our routine right here. Here's the interrupt routine. It loads up. You have to, whenever you get an interrupt, you have to acknowledge that you've done something with it before it takes on another interrupt. Okay, so we're going to acknowledge it. Remember, when it's in this interrupt, no other interrupt can occur. It won't accept the interrupt when it's in an interrupt routine. Okay. Read the interrupt status register, which is at FF92. We're going to check this bit to see if is it ours, because only thing we want to do here is look at that timer interrupt. Okay, if it's sometimes these read backwards, but if it's not equal to 0, it's for us. But we've got to remember we still got them turned off. Them timer ones we've said to do them, but we haven't started up. So it would fall through to this next instruction, and it would jump to the normal IRQ routine. Remember, if we look back up here, here's what that routine says. It goes to more so. Look up here. Here's what that routine says today, or before if we didn't copy it, it goes to 10C, and it's all down here we're doing. We're just continue on. It's not for us, it's for somebody else. Jump to 10C and do what you normally would do. So the system's sitting there running, the basic program's running. Any other interrupts come in, it's going to come here and go right back out. So that's we've got this whole thing knitted. Now we're done. Now you get back to the basic program and you're drawing your circle, do whatever you want, and then you hit the 2 out there that says start this system. Start printing this on the screen. It's going to end up here at this start routine, where the way we talked about how do we get here. We'll get here and we're going to load up 6C. This is going to enable the timer interrupt. Remember when we started up here, we disabled, right here, we disabled it. And down here, we're enabling it again. We're saying, okay, we want to get interrupts coming in from the timer now. Now, here's where it gets confused. We haven't started the timer yet. All we've done is told the system disable it. Now we're saying enable the timer, but we haven't started the timer, okay? I know it's confusing, but bear with me. So here's where we start the timer. The timer is a it's a 12-bit timer. Okay, 12-bit. This is an 8-bit machine. That's okay. It uses FF94 and FF95. In FF95, you have 0 to FFFF, and in FF94, you have 00 to FF. Okay, and once you store something other than zeros in 94, the timer will start. Okay, and that can be anywhere from a 1 to an FF, and 94 will start. Okay, so we're going to load the zeros up and store it in 95, the lower 8 bits of this timer. And we're going to load up D with 1F. We're going to use 1F. Why 1F? I don't know. I just grabbed it out of the air. I tried a bunch of them, but I think it was a good mix for what we're doing. Okay, if you get it just put a 1 in there. The timer comes on so quick you won't hardly get your basic program hardly run because there'll be so many interrupts from the timer that you won't get much done. If you put an FF in there, it takes a long time. You can play with that. Change this number and experiment with it. I mean, that's a good place to experiment with the time we'll do. Anyway, we're going to put a 1F and we're going to store it. We're going to start the timer. Okay, so now we've got everything going. The timer's running. The interrupts are turned on. Okay, now let's go to our routine. As soon as we started this timer, we're going to start getting interrupts that are for us. So let's go down and look at the routine again. Comes in. Tickle that, we read it. Is it for an interrupt from the timer? Yes, it is. Let's go to the routine called time in. Okay, now all this stuff we're doing, and this is the whole routine. It's all we're talking about, this little routine right here. We're going to load up something called timer count. Okay, we got some variables down here we use. Okay, we remember we started our address at 78, which is where our extra 8 lines are. We've got a speed, a color, a count, a delta, and a tilt. There are zeros other than deltas 1. Okay, we'll look at that. We're going to look at the timer count, which has a 0 in it, and we're going to add the delta to it, which is 1. So now we've got a 1 in A, and we'll store it down into our count again. Okay. Now the thing here, it says branch not equal. If it's not equal to 0, it's not. We're not going to do something. Return back. Only do something when it's 0. So we just made it. It was 0. We made it 1. We're going to go down here to return from interrupt. We didn't do anything. All we did was come in here and added 1 to it and went on about our business. Okay. So next time the timer kicks off again, we're going to come in. We're going to add 1. It's going to be a 2, and we're going to store it. It's not a 0. Don't do it. So what does that say? It says every 256 times the timer comes in here, it will do something. Not every time, but every 256 times. It has to get back to 0. It goes 0, 1, 2, 3, 4, 5, all the way to the FF. When it comes in with FF, we'll add 1, makes it zeros. We'll do something. So when it gets back after that 250 some odd times, we're going to do something. What are we going to do? We're going to load up FFA3. Remember what that is? That's where our blocks are in our telling the MMU which blocks we want to use. We want to load that up, and we want to save that original block number. We're going to load up our block 33. Okay, that's our block we're going to work with, and we're going to store it in there at FFA3, which now can be addressed at 6000 through 7FFF. Okay, so now we've got our block in memory. I'm going to slow down just a bit here and go back. And this is our configuration right now. Okay, we took what was in FFA3, which is 3B, we saved that, and we put a 33 in there. So this is our configuration right now with the interrupts turned off, because we're working on interrupts. So now we can address that block right there. Okay, now back to the show. Okay, now we got that. That's our configuration. Now we look up our timer color. Okay, and all it is just down here. It starts at a 0. Okay, we're gonna. We increment it by 1, and we bring it in, and then we mask off, and we only want the lower 4 bits, which is that's 0 through 15 or 0 through hex F. And guess what that is? That's the number of color palettes we got. We got 16 of them, so 0 through F is 16. So each time that we actually come through this routine, we'll use a different palette for a different color. That's how our colors get different on the screen. That'll be an A. We'll load up B with the hex 11 and multiply it. Okay, remember now we're working with 320 pixels across the screen, 2 pixels per byte, or 256 bytes. So in each byte we're going to have 2 colors. So if we multiply, let's say in our A, let's say we had 4. Use palette register 4. We load B at 1. We multiply it. We end up with a hex 4-4. So first pixel's a 4. The second pixel's a 4. So now we got both pixels. We got 2 pixels. We load up the timer address. Okay, remember it started at 7800, and we store what's ever in B, which is this 44, whatever the number, whatever the color palette is for them 2 pixels, and we display that. Finally, display that on the screen. We take and store the same thing on the screen. We're gonna A0. What is A0? Guess what? It's 160. Okay, because there's 320 pixels. I misspoke. There's 320 pixels or 160 bytes across the screen. I said 256. There's 160 bytes across the screen. A0 is 160 times 1, so it's going to go down 1 complete line and store that. The example I was using was the 44. We'll store it there. We'll go down another line, store it again. We'll do all 8 lines. We'll store that 44 example on the screen. So now we've got that rectangle box on the screen. We'll load up, add 1 to X, okay, because we start out at 7800. We'll make it 7801. We'll store X for the next time we come through here. We'll load up our original block up here. Remember, we're up here at this code here. We took this original block and we saved it, and we'll store it back in there, put the configuration back the way it was when it come to us, and we'll return from the interrupt and go back to basic and continue drawing its lines or circles. I'll make one comment while I'm here. Okay, what you might think, or what some people might say, and I did originally. Now I noticed. Okay, I originally loaded up this load A, this FFA3, which happens to be 3B. That's the original configuration, and I just did a push onto the stack because it's faster than doing this load store A, load A. I did a push and a pull. Well, only one problem. The stack is in FFA3, so I completely didn't have a stack. I was storing this temporary thing on we're pointing to the screen, so you got to watch out. There's no stack when you're in this routine, so don't use it. I don't want to. That's probably more confusing then. So that way we come through that. We're going back, and now we come back again the next time. Our count is 1. We've got to wait 256 times to do the same thing on the next 1 byte. 1 byte over, or 2 pixels over. We do the same thing, get a different color, go to the next color in the palette register, and just keep going through there. one other thing we can do here, not the only other thing, but one of the other things we can do is stop. Okay. If we come in and we say stop, what do? We disable, like we did before. First up, we disable that the MMU interrupts. Other interrupts are still available out there, but the MMU hierarchy, we just stop them. We load D with the zeros and we store them in FF94, which also stops the timer. So we've stopped both of them. It won't put out an interrupt and the timer isn't running either way. We come back in and we say start again. We'll do the same thing. It will enable the timer. We'll start the timer and it goes on about its business. All the other controls that we've got keep on going. Excuse me. All right, speed is another thing we had there. How do we speed this thing up? Okay, we'll come here via the basic command. We get the speed. First thing we want to do with speed, first thing we want to do is branch to the stop routine. We don't want to, because I'll try to explain why. We want to get it stopped. So we stop the timer and stop the interrupts from the MMU. I looked at this here and I don't know why I push X. I don't think I need to, or push and pull it, but anyway, it's in there. So we're going to reset the timer back to 0. The timer count, we set it back to 0. We want to increment the timer speed. Okay, the timer speed starts out down here at 0. Okay, that's where this is 0. We want to increment that and make that a 1. Okay, so we increment that and then we load up the timer speed, and all we want to do is get the lower 2 bits, the lower 2 bits, which means the only thing we'll have left in B is either a 0, 1, 2, or 3. That's our 4 options, okay? 0 was the first option, that's the normal speed. 1 is a little bit faster, 2 is a little bit faster than that, and 3 is a lot faster than that. So anyway, and we load up our speed table, which is right here. Okay, our speed table, if it's a 0, it would have a 1 in there, which means every 256 interrupts do something. Okay, remember we started out, it was adding that in there, one every time. The delta was 1 every time. It added 1 every 256 times, so it would do something. So if we put a 1 in there now, it would load up speed and add B to X. It would point to the second one in here. We'd have a 2, so the delta would be 2. So every time it comes through there, we'd add 2 to that counter, which would be 128 passes through there, will print to the screen. If we put a 2, okay, it would point to this one. We'd put a 4 in the delta, which means every 64 passes through there, up to the screen. And likewise, if it's a 3, add 3, that would point to here. Put an 8 in there, so every 32 interrupts that draw the screen. That's getting pretty fast, okay? So that's our speed table, 0, 1, 2, or 3. And now, likewise, when you get done here, it goes 0, 1, 2, 3. You put a 1 in there again, them 2 bits are going to revert back to 0. The rest of them, we're masking them out, so it would just keep rolling through there, okay? So that's our speed. What we got? We also got, well, let's just look at what we're here. Let's look at exit, okay? The very first thing, how do I do this? Let's look at message. We need to look at message first. Message is going to pass a new a variable, okay? That's a string variable. And up here I've got a note, register X has a pointer to a variable length and a +2 is a pointer to the variable. So let's get that confusing piece out here. In BASIC, if you pass a pointer, it passes to you, coming from BASIC, the variable, very first byte is the length. And this will say that, in this example here, press any key is the message, okay. The length would have 0D in there, or 13 bytes, because you can add them up. You got 5 and 6 plus 2, it makes 13. It have a 0D in there. And the actual pointer to the very first byte of that message is right here. That's what BASIC passes to you. So we load up the length as it passes to us. We load up the pointer to that message, which is 2 bytes in X. We save that length. We say, here's the column we want to use. We store it in the column. Here's the row we want to store it in that. We pull the length back up. And if you remember, in our other lessons, when we used BASIC to do the print, HPrint, we give it the column or row. We give it X was a pointer to the message, and B has the length of it. We jump over to BASIC to print that whatever passes on the screen. So in a sense, we've taken something for the keyboard into our assembly language program and went back over to BASIC to print it. So we got back to that, print it, and then go back to BASIC. Now let's look at exit. Exit, when it comes in, it's going to have a message there. And BASIC, I think the message was press any key. So first thing it will do, it will go up and it will print that message. We'll come back and then it will wait for the keyboard. Now this is inside our assembly language program. It's waiting for a character to come in from the keyboard. Once it gets a character, okay, it's going to do some things. It's going to all it's going to do is reverse what we set up when we did the init. And you can look at that. We're going to disable the interrupts. We're going to turn all this stuff off. We're going to restore our IRQ vector the way it was from 3 bytes and stop the timer and enable the interrupts again and exit out of there, and we're all done. Go back to BASIC and we're done completely. One other routine we'll go through while we're here is clear screen. Clear screen, you can say, why can we do H screen? H clear screen? Well, you could. There's only one problem. Let's go back and refresh our memories. I'll go back up here. Which one's best to use? All right, if you do a clear screen, an H clear screen, regardless if you're in a screen 1, 2, 3, or 4, which is BASIC's 4 screens you can use, it does a clear screen. It starts down here at the bottom of block 30, and it clears all the way through. It don't make any difference how much you're using. It clears all 4 blocks out. Okay, that's just nature of the beast. They don't put any extra code in there to say how far do I clear. Just clear it all, which means our line is in here. It was cleared out whenever you did a clear screen to refresh it, like when we're putting our menu on the screen, that clear screen, it would clear this all out. So we're gonna have to do our own clear screen, and that would be somewhere's in here. Why can't I find? There it is. Here's our clear screen. We're going to disable the interrupts. We're going to go to task 1. Remember what task 1 was? Let's just a refresher here again. I told you earlier we would use task 1 for something. That's right here. When we say task 1, this is the configuration we get. Our screen is in our blocks 30 is in here, starting down here to address 2000 up through 9FFF. Okay, so that's the address we got to work with because we're just going to use each screen. The task 1. Okay, and here it says our screen is from 2000 to 9800. Okay, because remember our too many numbers. Our basic screen ends at 7800. But we have our blocks loaded in at 2000, so now the end of our screen for BASIC is 9800. Okay, bear with me to think about it. Okay, but we're done. So we're going to load up 2000 in X. We're going to put 0 in D, and we're just going to sit here and loop through here until we get to 9800. Okay, 9800 is where our extra 8 lines start. So we're just going to go from 2000 to 98 and just clear them out. Bang, go back to task 1, turn arrows done, and we're done. That's our clear screen. That's why we use clear screen as opposed to BASIC's clear screen. That way it will not wipe us out. I think I've been through every routine. I'm sure I've got somewhat confused in there. I'm sure I misspoke a couple of times. I apologize because hopefully I catch it and put a disclaimer in there somewhere. But that's kind of it. The code is pretty simple. Actually, what's doing to the screen is getting the other thing is all set up. Go through, look at it, play with it, check with it. You can change some things, timer speeds and stuff like that. The basic program, there's not much in there. You can look at it. What I'm going to do though is probably in this. I don't know if I need a part 3 or not. I may have some other different tests to show you, but again, this stuff here was just a demo of what you can do. Okay, here's some things you must do. You must manually load LES 1 lesson 12 bin first. If you don't, you try to execute it, guess what? You'll be hung up real quick. Again, there's no error checking. Don't do the init multiple times. And don't exit before you init. Okay, remember I told you there was no error codes, no checking. It was just a demo program to show you what you can do. Here's your programming challenge. Try to make it bulletproof. I did the code for you, and I'll give you that code. But I think you should be able to come up with methods within the assembly language program and or the basic program. Is the assembly language program, is it loaded? Because if not, you're gonna blow up, you're gonna bomb. So somewhere you need to check somewheres in one of them in your basic program. Have I loaded the ASM program? Is the init complete? Okay, you're probably going to have to somewhere. And I don't tell you where to do it, because I mean I know where I would do it. But has the init been done? But if you can't do 2, 3, 4, 5, or 9 options if you haven't done the option 1. So I would somewhere, I think probably in the assembly language program, see some switch somewhere that says, hey, init's done, go on about our business. Likewise, don't allow it to init multiple times. Think about init multiple times. You do the init, and it stores the interrupt vector in our 3 bytes at the bottom of that program, and you don't exit correctly, and you init again, you're storing our init, our vector routine for the restore. Just think about what you would do if you init multiple times. And question mark, I don't know other errors you can come up with, but try to make the thing bulletproof. It's a challenge. I mean, because taking my code and using my code, hey, my code works. The challenge is learning how to program is to change this stuff and figure it out and work with it and say, damn, why didn't this thing work? And dig into it and figure it out. I think that's probably going to be it. Okay, I think I can get this done. I think I'm going to have some other examples that I've been working on using that very similar routine where it's doing multiple things. In fact, one of them is basic program displaying something, and it's displaying some sprites. Okay, just think about what you can do and work with it. Believe me, because this is, I think, what help a lot of basic programmers understanding how they can speed their program or do some neat stuff. Well, what about passing the numeric variables? Dig into the assembly language unraveled code and see what happens. I showed you what happens if you pass a string variable. You get the length and a pointer to the string. What happens if you get a numeric variable? How about passing something back? You can pass something back. Okay, it's very simple. You just have to work with it and say, oh, okay, I see that. It's done. Dig into the code. Yes, it's hard, but it doesn't get any easier by saying, God, I wish somebody would tell me how that's done. Dig into it and go with that. Okay, I've been rambling on long enough. That is kind of it. I'm hopeful that this is helpful to you. Questions, leave me an email at the gbj6809@gmail.com. I'll put that in the notes down there, and give me a like if you like this thing, so I know at least somebody's at least looking at this stuff. I don't know what they're looking at. In the past, past, they haven't looked at it that much, so I don't know if we'll have a lesson 13 or not, but let me know. All right, hasta la vista. See ya.